All right, so in this paper, we'll talk about the distributed redundant integration of the battery storage in data centers. So this is joint work with Asia at Microsoft. So of course, there's, for data centers, batteries are used fairly extensively, right? They're used as failover devices for on-site generation. And so data centers nowadays tend to be fairly big. And these batteries in data centers offer significant resources for grid services. For example, if you take, let's say, a 10 megawatt data center, then we'll have enough backup batteries for maybe 10 megawatt of battery backup for, say, 5 minutes or so. And if you look at the global power consumption of the data centers, it's about slightly more than 1%. So think of the batteries inside the data centers are there's a lot of power capacity in them. And all these batteries can be utilized for grid services. Then it's a pretty large set of resources, for example, for regulation services. So from a data center's owner's perspective, then the goal is always to balance profit with reliability and cost, right? So they own the batteries, and the batteries, their first job is to serve as backup for the data center. And then on the side, it may make sense to participate in the grid, right? So in this paper, so being backup in the data center is not as simple as just have the total energy available. I think this paper will look at a case where the batteries inside the data centers has to maintain the so-called N+1 redundancy. And subject to this constraint, how do we use them for the grid services? So the N+1 redundancy is really the same as in power system with, say, N-1 contingency, right? So if you look at the data center configuration, there typically is a number of batteries or UPS. These are the UPS serving different loads. And the idea is that if any of the single component fails, then all the loads should still be served, right? So for example, the first UPS may fail. There should still be enough capacity in the batteries 2 and 3 to serve all the loads. The loads are the servers, are the computing loads. Or that a distribution unit may fail, but then still you should have enough power in the leftover batteries to serve all the loads. All right, so it's really the same as the N-1 contingency constraint. Right, so then when we look at the amount of energy in the battery that satisfies these constraints, this is more dynamic constraints than, say, just summing up the total capacity available, right? So this depends on how the load changes. We need to make sure we have enough capacity in the battery, and this can change over time. So if you put into a grid service, really we're looking at something like a bi-level problem, right? On one level, the data center owner wants to maximize the profit, let's say being in a regulation service, but then needs to still satisfy the N+1 redundancy constraints. And then on another level, you need to figure out how much capacity, let's say, you should bid into the market, right? And thus, how much capacity you should bid depends on your load forecasting and how much load you think you will have. And all this together forms, you have to make a decision. And turns out we can write N+1 redundancy constraints fairly easily into a problem. We can solve this problem fairly easily in real time. So the conclusion is this battery has a lot of potential, right? But to extract this potential, we need to be mindful of their reliability constraints. And there are definitely other knobs you can play.